Welcome to a slow, beginner-friendly lesson on the float type, made for absolute beginners. Define floats only. Using them is next. We will not deep dive floating point edge cases, just the beginner meaning. Let us start from what we already know. The int type holds whole numbers, things like 1, 42, or -7. There is no dot, no fractional part. Integers are perfect for counting discrete things, people, apples, attempts. But the world is not only made of countable things. Some quantities live between the whole numbers, and that is where the int type runs out of room. We need a type that can hold a piece of something. Whole numbers only. Here is the whole idea in one sentence. A float is a number with a decimal point. That dot is the signature of a float. 3.14 is a float. -0.5 is a float. Even 2.0, which is mathematically whole, is a float in Python, simply because it carries that dot. The dot is what tells Python, treat this as a number that can have a fractional part, even when the fraction happens to be 0. The dot rules. Picture a ruler or a measuring tape. The big ticks are the whole numbers, but most of the surface is the space between them. Floats live in that in-between space. They let a program describe the world the way a ruler does, with all its fine gradations, not just the big marks. Between the marks, let us look at float examples in code. Pi, 3.14. A temperature of -0.5. A price of 9.99. And 0.0. Each of these carries a decimal point, so Python treats each as a float. When we ask for the type, Python says class float. The dot is doing all the work. Write a number with a dot and you have written a float, regardless of what digits surround it. Look for the dot. Why are integers not always enough? Because measurement lies between the whole numbers. A healthy body temperature is about 36.6 degrees, not exactly 36 or 37. A price is €4.50, not 4 or 5. A person is 1.75 meters tall. If we only had whole numbers, we would have to round every measurement to its nearest integer, and that throws away real information. Floats keep the detail. Measurement needs detail. Here is a detail that surprises many beginners. The number 2, written without a dot, is an int. The number 2.0, written with a dot, is a float. Mathematically they are equal, 2 equals 2.0. But in Python they are different types, because type follows how you wrote it. The dot is the rule. No dot means int, dot means float. This matters because the two types can behave slightly differently in arithmetic. The dot decides. Let us prove the dot rule with a type function. We ask for the type of 2, and Python says class int. We ask for the type of 2.0, and Python says class float. Same digits, different answer, all because of the dot. And just to be thorough, 2.0 wrapped in quotes is text, a string, not a float at all. The type function never lies. Whenever you are unsure what kind of value you are holding, ask for its type. Ask for the type. Think of a scale balancing two sides. On one side sits the number itself, on the other sits its type. 2 and 2.0 balance perfectly as values, yet they are made of different stuff. Python cares about the stuff, not just the weight, so it keeps them apart by type. Same weight, different stuff. You may wonder where the name float comes from. It is short for floating point. The idea is that the decimal point can float, it can move left or right to represent very large or very small numbers. You do not need to remember the underlying math. Just know that float is the name Python, and most programming languages, use for numbers with a fractional part. The name is standard, so you will see it everywhere you go. Floating point. Where do floats show up in real programs? Almost anywhere the real world is measured. Prices and money, because cents live after the dot. Temperature readings from a sensor. Percentages and ratios, like 0.5 for half. GPS coordinates, latitude and longitude, are floats because positions are continuous, not snapped to whole degrees. Anywhere a value can land between two integers, a float is the natural choice. Measurement of every kind. Here is a float doing real work, a price calculation. We set a price of 9.99 and a tax rate of 0.21. The total is the price plus the price times the tax. Every number here carries a fractional part, so the whole calculation stays in floats, and the result, 12.0879, is a float too. This is exactly the kind of arithmetic a shop or a billing system does millions of times. Floats make monetary and scientific math possible. A float at work, a whole and a half, joined by a dot. That is the shape of a float. Two ideas in one number, the countable part and the fractional part, written together. It is a small invention, but it lets programs describe a continuous world instead of chopping it into crude chunks. Whole and fraction joined. Let us nail the writing rule with examples. 0.5, 3.0, negative 12.75, all floats, because each has a dot. The number 5, written with no dot, is an int. If you want 5 as a float, you must write 5.0. It sounds fussy, but it is consistent. The dot is the one and only signal Python uses to decide. Get comfortable writing the dot and you will rarely be surprised by a values type. The only signal. Floats can be negative just like integers. Negative 0.5, negative 3.14, negative 100.0. The minus sign always comes first, before the digits and before the dot. The rule is simple: sign first, then the number, then the fractional part. Python handles negative floats exactly as you would expect from ordinary arithmetic. Nothing changes about the type, the dot still makes it a float. Sign first, then the dot. Floats stretch across an enormous range. A float can be as tiny as 0.0001, or as large as 1,000,000.5, and everything in between. That is the floating part of the name at work. The decimal point shifts to keep the number representable. You will rarely hit the edges in everyday code. Just know that the float type covers both the very small and the very large, which is one reason it is the default for real number math in Python. One type, wide range. Measurement is full of operations. Add a little, take a little, scale up, scale down. Floats are built for exactly that kind of work. They carry the fractional detail through every calculation, so the result stays close to reality instead of collapsing into round numbers. Built for measuring, let us draw the line clearly between int and float. The int type holds whole numbers, written with no decimal point. The float type holds numbers with a fractional part, written with a decimal point. Both are numbers, and they cooperate well in arithmetic, which we will see next. But they are distinct types. The dot is the dividing line. No dot means int, dot means float. That single rule answers most beginner confusion. The dividing line. How do you choose between int and float? Ask one question. Are you counting whole, indivisible things, or measuring something continuous? 3 people is a count, use int. 1.75 meters is a measurement, use float. 12 attempts is a count. A temperature of 20.5 degrees is a measurement. The task itself tells you the type. You rarely have to think hard about it once you internalize the question, count or measure. Count or measure. Let us see the count versus measure choice side by side. We count 3 people, so people is an int. We measure a height of 1.75 meters, so height m is a float. When we print both types, Python confirms it, int for the count, float for the measurement. The decision was made the moment we wrote the values, dot or no dot. This is the simplest, most reliable way to think about which numeric type to reach for. Side by side, a common beginner confusion is mixing up 0 the integer, 0.0 the float, and none which we meet soon. They are all different values with different types, even though they might feel similar. 0 is a count of nothing. 0.0 is a measurement of nothing. And none means no value at all, not even 0. Being intentional about the dot, and about which type you mean, prevents a surprising amount of subtle bugs later on. 0 is not always 0. One honest warning, which the next lesson unpacks fully. Floats are an approximation of real numbers, and they can carry a tiny invisible error. The famous example is that 0.1 plus 0.2 does not land exactly on 0.3. For everyday counting and display this rarely matters, but it is the single most important thing to know about floats before you do serious math with them. We will understand why, and how to handle it, very soon. More on this soon. Let us hold the lesson together. A float is a number with a fractional part, marked by a decimal point. The dot is what makes it a float, regardless of the digits. 2.0 is a float even though it is whole, because it carries a dot. We reach for floats when we measure the world, temperatures, prices, distances, anywhere a value can fall between whole numbers. If those sentences feel true, you understand what a float is. 4 true sentences. The takeaway, compressed to one rule. A float is a number written with a decimal point, and that dot is the one signal Python uses to give it the float type. Whole numbers without a dot are ints. Numbers with a dot are floats. Reach for floats whenever you measure rather than count. In the next lesson we put floats to work in real arithmetic and meet the most famous surprise in all of Python. Take a breath, you just learned the float type. One rule to remember, every measurement rests on a foundation of fine detail. That foundation is the float. Whole numbers give us the frame, but floats fill in the world between the marks. Without them, programs could only count, never truly measure. With them, code can describe reality as finely as we need. Thanks for watching. Next, using floats.